Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Hello, Mr. T here with a tutorial on increasing and decreasing intervals of functions. This is the first in a series heading towards our ultimate objective of being able to sketch the graph of a function, even relatively complex functions, using a combination of algebra and calculus skills, and to be able to do that without the aid of a graphing utility. So we're going to be starting today looking at certain aspects of functions. And before we get into the math and the calculus, let's look at an example of a function I have graphed here. And this function, what we're interested in the first segment here, is where the function is increasing and decreasing. So what I mean by increasing, as we're heading values for x going left to right, so as the x values are increasing, what are the y values doing? So in this range here, the y values as we go left to right are decreasing. So this part of the function is decreasing. When we get down here, now the function is increasing. And it flattens out temporarily and continues to increase. And then over here, again, as we're heading left to right, again, it's decreasing. Now, our ultimate objective is to be able to find the intervals, meaning the x intervals. So on this one, it's going to be from negative infinity to this x value here, 1, is decreasing. So that interval is decreasing. From negative 1 over to here, it's increasing. And then from here to this point here, it's also still increasing. So this is increasing, this is increasing, and then from this point out to infinity, it's decreasing. So we're going to look at how can we figure that out using without having to look at the graph. So let me clear off my writing here quickly. Now, one of the things we might notice with this graph is if we looked at, in this interval here, we said it's decreasing. If at any point in this interval, if we sketched a tangent line, the slope of that line is negative. So the slope of that line is negative. And remember, the slope of that tangent line would be found by finding f prime of x. So all along that line where it's decreasing, our derivative is less than 0. It's negative. At this point, if we drew a tangent line, it's a horizontal line. Its slope is 0. So at this point, exactly at this point right here, our f prime of x, which is the slope, equals 0. And here, if we drew a tangent line, say I'd put one here, that line has a positive slope. So here, f prime of x is greater than 0. And again, at this point, we have a horizontal tangent line, so we have a slope of 0. And over here, we would have tangent lines that have negative slope. So we're going to use that fact where based on the slopes of the tangent lines, we can find where the function is increasing or decreasing. So let's formalize this mathematically. So again, our objective is to write intervals, meaning interval notation, on a function where the function is increasing and decreasing. So a function is increasing on an interval if during that interval f of x has to be defined, so you can't have parts of that interval where f of x is undefined, maybe a asymptote or such, and it has a positive derivative. And it's decreasing where the derivative is negative. Obviously, it has to be where the function is defined. As we saw, the boundary between going from decreasing to increasing, we instantaneously had a point where the slope was 0. So that's going to be one of the keys to finding our boundaries between increasing and decreasing intervals. So the boundaries where the function may change. So these boundaries, these values we're going to find won't always have a change in increasing, decreasing, but if it changes from increasing to decreasing, it will be at these values. And we'll be referring to these as critical values. They're also sometimes called critical numbers. And the way we find critical values for a function are three things that we look at. So we look at the values that make the derivative equal to 0. We look at it where the derivative is undefined. Or we also will be looking at places where the original function is undefined. So we'll be looking at those three situations to make a list of critical values. So our process, if we're given a function, now this is the equation of that function that was graphed earlier. The process to be able to write the increasing and decreasing intervals are these three steps. We're going to find critical values first. And then similar to what we did with solving function inequalities, we are going to be organizing those critical values on a number line and testing in each interval whether the derivative is positive or negative. And based on that, we can then determine where the derivative is positive, it'll be an increasing interval, and where the derivative is negative, it will be decreasing. So let's go through this example. So to find critical values, we have to look at three things. So the first, we said we want to find where f prime of x equals 0. So we've got to find f prime of x. So if we take the derivative of this, we've got negative 15x to the fourth plus 15x squared. That's a 15, sorry. And we have to solve that for equal to 0. So we're going to solve by factoring. So I can GCF factor out a negative 15x squared. And I would be left with x squared minus 1. And if we set that equal to 0, we get x equals 0. And if we set this equal to 0, I'm going to get x equals plus or minus 1. The second way of finding critical values are any values that make this derivative undefined. Well, this is a polynomial. It's defined for all values, so there's no places where the derivative is undefined. And the third we look at would be where the original function was undefined, but this function is defined for all real numbers. So our critical values are 0 and plus or minus 1. So we're going to organize that on a number line. And we're going to test in each interval. And what we're going to be testing is not the original function. We're going to be testing the derivative. So if I pick a test point in here, let's say negative 10. If I put negative 10 into my derivative, I put it into the factored form. So negative 15 times negative 10 squared. Negative 10 squared is going to be 100. But negative times positive is going to be negative. So that factor gives me negative. And if I put negative 10 in here, negative 10 squared is going to be a big positive number. So this factor will be positive. So we have negative times positive. Our derivative is negative. Put that down here. Negative means the function decreasing. So I like to show it with a line here, meaning that the function is going downhill during this interval. Now let's test a point. Let's say we could test 0.5, negative 0.5. Again, negative 0.5, this is always going to be positive. Negative times positive is negative, so the first factor is negative. Now 0.5 squared is going to be smaller than 1, so this part here will be a negative number. So we have negative times negative. That gives us positive. So that means in this interval the function's increasing. Put in positive 0.5, so I've got, again, that part's going to be negative. And this part, a positive 0.5 squared is less than 1, so that's negative. So again, we're positive, so we're increasing. And finally out here we've got negative, and then this will be a big positive number, so we have positive, so this will be negative. So our intervals for increasing, if we write that first, will be from negative 1 to 0, and then from 0 to 1. And for decreasing, we've got from negative infinity to to negative 1, and then from positive 1 to infinity. So let's go back to our diagram and make sure that matches our picture. So from negative infinity to negative 1, we're decreasing. Then from negative 1 to 0, we're increasing. 0 to 1, we're increasing. And 1 to infinity, we're decreasing. So that matches our graph. So let's look at another example. So let's look at this one. So first, let's look at find f prime of x. So we've got the derivative of that will be 2, and here I've got to take 2/3 times negative 3, which will be negative 2, and then we're going to subtract 1 from the exponent. And I'm going to GCF factor out a negative 2x to the negative 1/3. So I would be left with here x to the positive 1/3 power. I'm sorry, I'm going to take out a positive of that. So this would be x to the 1/3, and this would be negative 1. And finally, I'm going to move this to the denominator. So our derivative is 2 times x to the 1/3 minus 1 over x to the 1/3. And we want to find our critical values, so we set that equal to 0. Well, to solve a rational equation equal to 0, we're looking at the numerator equal to 0. So we're solving x to the 1/3 minus 1 equals 0. So to solve a radical equation, we get the x by itself. And this time we cube both sides. And here we get x to 1 to the cubed is 1. That's the only value that makes our derivative equal to 0. Now also remember, we need to look at our derivative undefined. This would be undefined if we divide by 0. So if we set the denominator equal to 0, we get x equals 0. So that's also a critical value because it makes the derivative makes the derivative undefined. And lastly, we look at our original function. Nothing makes that undefined. This x to the 2/3 is defined for all real numbers. So our critical values again here were two of them, 0 and 1. So let's put them on a number line and look at our 3 intervals. Look at test points, and we're going to plug it back into this derivative. So this 2 is positive all the way across. Now if I put negative number here, negative number to the cube root of a negative number is negative, so this is going to be negative. And on the bottom, this will be negative. So positive, negative, negative, we have positive, so we're increasing. If I put in, this was 1 here, sorry. If we put in 0.5, cube root of 0.5 is smaller than 1, so this is negative. And the cube root of 0.5 is a positive number. So now we're decreasing, and here we would be positive, positive, positive. So we're increasing. So our increasing intervals are from negative infinity to 0 and from 1 to infinity, and decreasing is from 0 to 1. Now I sketched a graph using a graphing utility of this function. It looks like this. So you can see here from negative infinity to 0, we're increasing. For a short period of time, we're decreasing, and then we're increasing. Now this point here, remember, 0 made the derivative undefined. This sharp point here is called a cusp, and we could draw an infinite number of tangent lines at that point. That's what causes our derivative to be undefined. And lastly, our last example here, let's look at a function like this. So we want to rewrite this in order to do our derivative. So this would be x minus 2 to the negative second. So if I find f prime of x, I've got negative 2, x minus 2 to the negative third power times the derivative inside, which is 1. So we've got negative 2 over x minus 2 cubed. If we set that equal to 0, there is no value that makes that 0. So for f prime of x equal to 0, there's no solution. But the derivative as well as the original function is undefined at x equals 2. So we have a critical value. Our only critical value is x equals 2. So if I put a negative number into the derivative here, I've got negative on top. And on the bottom, if I put a negative number in here, I've got a negative number cubed, which will be negative. So we've got negative over negative, which is positive, so this is increasing. And over here, if I put a negative number, I've got a negative on top, and if I put a big positive number here, this will be positive, so we are decreasing. So the function is increasing from negative infinity to 2 and decreasing from 2 to infinity. If we look at a graph of that function, we have a vertical asymptote at 2. So over here we're increasing, we have positive slopes. Over here we're decreasing, so that matches what we found. Now on our functions, besides increasing and decreasing, let me go back to say this picture here. The other thing we're interested in are these points right here, that point and this point. These are referred to as relative extrema. So for example, this point is a relative maximum. It's not the maximum of the function because values of y over here go up to infinity. So this is not the biggest value of y in the function. But in its neighborhood, in this area around that point, this is the highest point. So that's why it's called a relative maximum. It's not an absolute maximum. Same thing over here. This is not the lowest value of the whole function. That would be over here. It heads to negative infinity. But in this neighborhood, it is the lowest value. Now, one thing you might notice is that on both of those points, if we drew a tangent line, the slope of that tangent line is 0. So relative extrema will always occur where the derivative equals 0. So again, I showed you graphically what the relative extrema are. There's two kinds. There are relative maximums and relative minimums. And it's a relative maximum. This is essentially the mathematics here that says in the neighborhood of point C, our function is the values of x around point C are smaller, and over here they're bigger. And again, the key thing is that these relative extrema occur at the critical values. So to find relative extrema, we do two things. We find the critical values, but then what we have to have is we have to have an increasing, decreasing pattern on each side of the derivative. So we're going to be looking, since I use lines on the number lines, when we have going up and then down around a critical value, that's going to be the signature for a relative maximum. And when we have it going down followed by up, that is going to be a relative min. Once we know the x values, to find the y values, we plug it back into f of x. So let's go back and look at our examples. And this time, instead of finding the increasing, decreasing intervals, let's find our relative extrema. So here are our critical values. At this point, we're going down, up, so this is a relative minimum. Here, I have a critical value, but I don't change directions. I'm going up and up, so this is not a relative extrema. At this point, I was going up and then down, so this would be a relative max. So we have a relative min at x equals -1. And to find the y value, we would have to put -1 in this equation. So if I evaluate f of -1, I've got -3 times -1 to the 5th plus 5 times -1 cubed. This is -1 times -3 is +3, and this would be 5 times -1, so that's -5, so we're at -2. So our relative min is here, and our relative max happens at positive 1. If I put positive 1 in here, I've got negative 3 plus 5, I get 2. And if we look at our picture, this coordinates of this point here is negative 1, negative 2. That was our min, and our max here. Now you can see at this point we had a temporary horizontal tangent line at that point, but we did not have a max. This later we'll learn is called an inflection point. Now, relative maxes can also occur at places where the derivative is undefined. So when we look at our cusp problem here. So again, we've got a pattern here of increasing, decreasing. So this is a max. And we have a decreasing, increasing. That's a min. So our coordinates for our max are at 0, comma, and if I put 0 in here, I've got 0 minus 0, so it's 0, comma 0. And our min is at 1, comma, and if I put 1 in here, I've got 2 minus 3, I got negative 1. And again, if we look at our graph, this is a max, it's at 0, 0, and this was our min right here, and that's at 1, negative 1. Let's look at our last example. Now here, this looks like a max, but if we go to put that value into the original function, it's undefined. So this is not a relative maximum. The y value at the point has to be defined. And if we look at our graph, both of these are going up to infinity and they never touch this line. So it doesn't like go up there and bend over. This goes to infinity forever. That goes to infinity. So this function, and there's no other places where we have that bend, so there are no relative extrema on this function. So I hope this helps. We've talked about how to find increasing, decreasing intervals and how to find relative extrema using our first derivatives and critical values. So good luck in working your problems.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready?